All right, 3.5, we're shifting gears just a little bit. We're going to talk about limits at infinity. So we're going back to discussing a little bit about limits in this section. So first of all, definition. So let L be a real number. The statement, the limit as x approaches infinity of f of x equals L, means that for each epsilon greater than 0, there exists a capital M such that f of x minus L is less than epsilon whenever x is greater than m. And I'm not going to make you memorize it. We're not memorizing them. I know. I knew that was the next question. We're not memorizing them. And then we have the corresponding sort of other statement for what happens on the other side. The statement f of x, or the limit as x approaches negative infinity of f of x equals L means that for every epsilon greater than 0, there exists a capital N less than 0, such that f of x minus L is less than epsilon whenever x is less than n. So what this is really hopefully hearkening to as we move in this section is we're looking at horizontal asymptotes. Okay? So vertical asymptotes we've been discussing all along, right? They're going to be vertical lines we get close to, we don't cross them. We have values that give me zeros and denominators, things like that. Horizontal asymptotes are a little messier to work with, but the visual is much the same. So all this is saying is that if I had a horizontal asymptote that I'm getting close to, and I'll just draw one half of it, and I'll just draw it at x equals 0, y equals 0 that we're approaching, is that no matter how close you want to get down here, right, your graph is continuing to get closer to, in this case, the x-axis, right? That's what this limiting process is saying, is that no matter where you sort of draw this line, you're getting even closer to that specific y value, that specific limiting value, okay, infinitely close. And in particular, that's why we see horizontal asymptote showing up as our next definitional piece. That line y equals L is a horizontal asymptote of the graph of f when the limit as x approaches negative infinity equals L or positive infinity equals L. We have horizontal asymptote. Horizontal asymptotes are interesting because actually you can cross them sometimes in the middle of them. It's the extreme behaviors that we're actually talking about when we're talking about horizontal asymptote behavior. What happens on the edges of the graph? What happens as we get further along on the edges? There's a couple of things that you've seen with horizontal asymptotes before. Usually when you see horizontal asymptotes before calculus, you see them for rational functions, right? Functions that look like, 3x squared plus 2x minus 7 over 3x cubed plus 4x plus 2 or something, whatever. You've got a polynomial over a polynomial, and we look at the ratio of the coefficients or something like that. We look at the exponents and the ratios of coefficients. And they do show up in there, but they show up in other places as well. In particular, we're looking at this from the perspective of limits. So if r is a positive rational number and c is any real number, then the limit as x approaches infinity of c, any constant, over x to the r is 0. Furthermore, if x to the r is defined when x is less than 0, then it works on the other side too as x approaches negative infinity. This is going to be like the critical spot that we need to get to in every problem we work at in this section. We're looking for things to have constant on top, x to a power on bottom. Constant on top, x to the power on bottom. That's what we're looking for. So let me show you what happens as we take a look at this. This wants us to find the limit as x approaches infinity of h of x. And it's taking a function that's just a polynomial, 5x cubed minus 3x squared plus 10x, and it's going to be dividing it by different powers of x. So if you flip from this one, say, to your next page, so this one's dividing by x squared, and then the next one divides it by x cubed, right? We're just looking at different powers of x that we're dividing by, making a comparison on this first example. So what we're first going to do is just to rewrite what we have here. So if I rewrite this, this says that I have 5x cubed minus 3x squared plus 10x, and I'm dividing by x squared. Okay? And what we're actually going to do is what Alyssa was talking about on the earlier question from last section, where she said, can I just divide each of those pieces, and then I can do my derivative from there? You guys remember that? And I was like, yeah, you can do that. Well, we're actually going to do that. Like, that's what we want to do here. So see, you were just ahead of the game today. So we're going to divide each of these individually by the denominator x squared. I'll write it out specifically so that when you're looking back, you're not like thinking, where did we go next? We're dividing them out individually. Okay, so this is the same thing. It's just written differently. And of course, as we do that, some of these collapse. So this is going to give me 5x on the first one. The second one is minus 3. And the last one is going to be 10 over x. Right, this is just algebra. We haven't done any calculus yet. We've just done an algebra step. But in particular, what we're wanting to do is we're wanting to take, back up here in the directions, the limit as x approaches infinity. So if I take the limit as x approaches infinity of this expression h of x, right, then I'm taking the limit as x approaches infinity of, I'll use the last version that I created, right, 5x minus 3 plus 10 over x. And in particular, what we see happening here is that this piece right here, according to the definition that we saw over here, will go to 0. That's really what I'm trying to get to the point of here. Now, the others don't, right? Whoops, sorry, with the wrong direction. These don't have that form, right? 5x and 3 don't have the form of the previous theorem, but this piece does. And one of the things that we did quite some time ago, like chapter 1 kind of stuff, is we said, okay, well, if you have the limit of a bunch of things, you could separate out and do the limit of each piece individually, right? So while you don't necessarily need to write it on each one of these, what this is really saying is that we're going to do the limit as x approaches infinity of 5x plus the limit as x approaches infinity of negative 3 plus the limit as x approaches infinity of 10 over x. Okay, so I don't need you to write this out for me every time. We've already done this before. But that's what's really happening. So this last piece, 10 over x, goes to 0, right? This one approaches 0. But each of these do not, in particular, right? The first one, what happens when I put the infinity in here? Yeah, 5 times something that's getting infinitely bigger is getting infinitely large, right? This is infinity. What about the negative 3? It's negative 3. So I've got something that's infinite, to which I'm subtracting 3 and adding 0. This is an infinite limit. So if you want to show or to think about it from this perspective, you can. But this is sort of like an aside. What you can do right here, if you're working at it from like, oops, what does she want me to show? That would be 0, right? This piece goes away. This piece is negative 3, but the 5x is infinity. So this whole limit on this particular problem is infinity because of the 5x. Basically, the 5x is dominating everything, right? Something that's getting infinitely large is going to overpower the negative 3 and the 0. But what I'd like you to see is what happens when we divide by x cubed instead. Because it matters what you divide by. You might think x squared, x cubed, I'm just dividing by a power of x. How much difference can it make? Well, it can make a lot of difference. So if we do the same thing that we just did before, but we have x cubed now, so 5x cubed minus 3x squared plus 10x, and we divide by x cubed. This time, and I'm not going to write out the individual pieces because we did that once already, but I have 5, right? And then I have minus 3 over x. And then I have plus 10 over x squared. Okay, so I skipped all the algebra to get there. Does anybody need clarification on any of those pieces? Please ask if you do. Do you see where each piece came from? Okay, so there's the algebra simplification, and then there's the calculus, which is the limit part. So we're doing the limit as x approaches infinity of that quantity, 5 minus 3 over x plus 10 over x squared. And what we know from the limit piece over here is that both of those last ones have that form. They're a number over x to a power, right? Both of them are. So each of those goes to 0. And what's left is 5. Now, think back to what you remember from college algebra or algebra in high school or whatever the last kind of algebra, strictly algebra class is that you had. If you were to have looked at this equation right here, this expression anyway, and you were to have used rational functions as your basis point, the degree on the top and the degree on the bottom, they match, right? So what we did back then is we said, okay, look, the degree on top and the degree on bottom are the same. So we look at a ratio of the leading coefficients. And the leading coefficient on the top is 5. And on the bottom, there's an understood here, 1. 5 over 1 is 5, and that's the exact same thing you're seeing showing up from a calculus standpoint below. It's still 5. It's a horizontal asymptote. There's a horizontal asymptote at y equal 5. Okay, so we're going to do a couple more. All the time we're going to be trying to get these things that show up being 0. So as we look at these last few, they should go pretty quickly. The problem is that they don't always just have a single divided by x, right? This one, we got like other stuff down there, yeah? Well, what I want is I want as many of those pieces going to 0 as possible. So here's what we do. We will take the biggest exponent, x cubed, and we are going to multiply every piece by 1 over x cubed. That's the algebra step we're going to do every time. So the limit is x approaches infinity of, and I have to distribute, right? You guys are good at algebra, so we can do this. So I have 3 over x cubed. Move this down a little bit. I have 2x over x cubed, which is 2 over x squared. I have 3x cubed over x cubed, which is 3. And then I have 1 over x cubed. Okay, so that's horribly messy, and I get that looks atrocious, but it's exactly what we want. Because every piece that says constant over x to a power is now got a limit of 0. Lots of zeros. This one is 0, this one is 0, and this one is 0. So what I end up having, truly, is 0 over 3. What's 0 over 3? 0. So right before it becomes like horribly, and you're like, oh no, it's exactly what you wanted. It's exactly what you wanted. So we do the same thing again. Now this one makes it look like, oh no, now there's an x squared underneath a radical. That's okay. What's the square root of x squared? It's just x, right? So while it looks like I've got a square root of x squared, that's really just basically having x in the denominator equivalently. So what I'm going to do to compensate is I'm just going to multiply each of them by 1 over the square root of x squared. And each of those pieces can transfer in. So on the first one, we have x over the square root of x squared. Well, this square root of x squared, this is just 1 over x, right? Are you guys good with that? Mm-hmm. Right? So when I multiply it by the x on top, I just get 1. When I move it underneath the radical with the square root here, this gives me 1. And when I move that underneath here, I have 1 over x. Okay? This one's kind of funny looking. I know I'm out of time. I'm sorry. I'll pause just a second, and then I'll finish the last piece up in a second video. But this would be just 1 over, just be x over x squared. That's giving me the 1 over x. The limit at the front still stays limit until we've done it, just like we did back in chapter 1. It's an infinity. This piece goes to 0. So now I have 1 on top, and what do I have on bottom? 1. So this one's overall limit is actually 1. Okay, so I'm going to pause this. I'm going to let you guys leave the room, and then I'm going to pick up and finish the last little piece so that you can hear it, and you can just, chime in on the video later for the last 3 minutes or something like that to finish it, okay? Have a lovely weekend, and both of these assignments will be due And then we have a quiz on Monday as well. It's 3-4, 3-5 quiz Monday. All right, so if you're coming back to join me, we didn't finish example 4 in class today, but I wanted to finish it up so that you could see. It is a little bit different because of the trig function involved instead, but it's an interesting kind of difference. So one of the things that we know about trig functions, in particular sine and cosine is what I'm referencing, is that sine and cosine are bounded, right? They bounce up and down, right, like this, and they also have sort of this 1 and -1 showing up every time they oscillate. So they're a bounded function when we're looking at sine and cosine. So in a very real sense, it's true that -1 is less than or equal to the sine. In this case, I'm going to write sine of 2x because that's what our function is less than or equal to 1. That might not seem to be very important, but it will be in a moment. But it's a true fact, right? It's a true fact from trig is that the sine function goes between -1 and 1. What I can actually do then is that as long as my x value is positive, which it is because it says x is approaching infinity, right, is that it's equally true for me to be able to divide each of these by x, right? So now I have closer to what's inside of my limit. I know that my -1 over x is less than or equal to sine 2x over x is less than or equal to 1 over x. But if it's true all the time, it's true for their limits as well. So the limit of -1 over x as x approaches infinity is less than or equal to the limit of sine of 2x over x is less than or equal to the limit of 1 over x as x approaches infinity. Why does it matter? Well, the reason it matters is because these two that are sort of sandwiching it in, this is called the sandwiching theorem, by the way. These two that are sandwiching in my limit both exactly have that form that we discussed over here before. There it is, right? They're both a constant, right? C is any real number, doesn't matter if it's positive or it's negative, and they're divided by x to a power. So what does that mean? Well, it means that the limit over here on the left is 0, and the limit over here on the right is 0. And the only way that sine of 2x over x is going to be in between 0 on the left and 0 on the right is if its limit is already 0 as well. So this is sandwiched, right? It's sandwiched in between a lower bound of 0 and an upper bound of 0, which must mean that this also equals 0. So these 3 dots you'll see in mathematical literature sometimes mean therefore. So therefore, this means that the limit as x approaches infinity of sine of 2x over x must also equal 0 because it's sandwiched in between 0 and 0.